Okay, this is section 19.3, the standard reduction potentials. This is an important section for figuring out how to analyze galvanic cells. So that's what we're going to work on doing here. Oops. Move that back over here. Sorry. There we go. Okay. So let's begin by considering what is called the standard hydrogen electrode. This is often abbreviated as SHE, standard hydrogen electrode. In order to measure electrical voltages or electrical currents, we need two electrical connections. So if you think about a battery, for example, a battery has a positive terminus and it has a negative terminus, right? So any kind of battery you see has a polarity to it. This is called polarity. Okay? We can think of this as, in a sense, a measure of the direction that the electrons move in a circuit. So for example, let's suppose we have a wire attached to this battery. Essentially what we could claim is that the electrons are flowing through this wire out of the battery and then back into the battery from the negative to the positive. So there's a directionality to that, right? The electrons are flowing in a particular direction. Okay, and that's called polarity. There's positive and there's negative. So if we have a battery and we disconnect one end of it, the battery will cease to function, right? It doesn't work. If you've ever put batteries into a device and you realize, oh, I put them in the wrong direction, you could have a device with 6 batteries, but if you put one of them in the wrong direction, you have to take that battery back out and put it in the correct direction. So the polarity is an important aspect of electricity. Now, if we want to measure the voltage or the potential of a battery, or of a galvanic cell, because remember a battery is a galvanic cell, we need to connect it at 2 points. We need to have a positive terminal and a negative terminal. Okay? The positive terminal in a galvanic cell is the cathode. And the negative terminal is the anode. Okay? And remember we said that the cathode is where reduction is occurring. And the anode is where oxidation is occurring. Okay? Now here, let's come back to our standard hydrogen cell. The standard hydrogen cell is designed to allow us to make a table of what are called standard potentials, standard reduction potentials. And we'll get into that in a moment. But let me show you how it's constructed. It's very simple. It involves an aqueous solution of hydrochloric acid, HCl, at a concentration of 1 molar. Okay, that's an important aspect of it. It has to be at 1 molar. Okay. It also has hydrogen gas flowing through at a pressure of 1 atmosphere, 1 atm. Okay. It has a platinum wire right here in the center. That platinum wire is there for electrical conductivity, and when we measure the voltage of this cell, we're going to connect it to that platinum wire. Platinum wire is used because it is, for the most part, electrically inert, meaning it does not undergo any redox chemistry. So it will conduct electrons, which is essential for measuring the electricity, but it doesn't itself get involved in any chemistry. Okay? So that platinum electrode, see all the way down at the bottom, there's a big chunk of platinum? that right there is where the chemistry is occurring. The reaction is occurring. It could be a reduction reaction or it could be an oxidation reaction. So that's what's kind of interesting about the choice of the standard hydrogen electrode over another type of electrode, is that hydrogen undergoes, for reduction, the reaction looks like this. 2H plus 2 electrons becomes H2 gas. So that's what happens if it gets reduced. If it gets oxidized, it does the opposite. H2 becomes 2H plus and 2 electrons. Okay? So you can't tell from this picture easily what's happening because hydrogen gas is being bubbled through. So there's our hydrogen gas coming at the top at a pressure of 1 atmosphere. And then there's hydrochloric acid down at the bottom in the solution. So you don't know which direction it's going. It could be going under reduction or it could be going under oxidation. And it turns out it depends what it's connected to. So here's a picture of two possible setups using the standard hydrogen electrode. On the left is a zinc electrode, so a piece of zinc immersed in 1 molar zinc 2 ions in solution, right? It's in water. Connected to a salt bridge. And then on the right is the standard hydrogen electrode, SHE. Okay? Notice the voltage there, 0.76. The fact that that is positive and the platinum is connected, the standard hydrogen electrode is connected the way it is, we'll get into this in a bit, suggests that the hydrogen is being reduced and the zinc is getting oxidized. Okay? So on the left, hydrogen is getting reduced, zinc is getting oxidized. So what's happening chemically is, at least for the hydrogen, that's happening. It's getting reduced. The one on the right, the diagram on the right, is the reverse. Here, the copper's getting reduced and the hydrogen's getting oxidized. Okay? It's not clear from the picture how to tell that. It's just a limitation in terms of how they drew this, but a clue is this. This is the information you need. On the left, if you look to next where it says anode negative, the zinc is negative. The fact that it's negative means that it's the anode, which means that it's oxidation. And so the other one's got to be positive. It's got to be reduction. It's the cathode, right? The hydrogen on the right. If you look at the diagram all the way to the right, there's a positive next to where it says cathode copper up at the top. That tells us that the copper is undergoing reduction and that the hydrogen is undergoing oxidation. Okay? So that's not obvious from the pictures, but that's what's happening. It says, hey, copper's positive, so that means it's reduction, so that means hydrogen is oxidation. And then the one on the left, the anode zinc is negative, that means that that's oxidation occurring there, so the hydrogen is getting reduced. Okay? So those are two of these cells. These are called cells or galvanic cells, and they are generating electricity. The one on the left generating a voltage of 0.76 volts, and the one on the right, 0.34. Now, what that allows us to do, that hydrogen, the standard hydrogen electrode, is it gives us a way of making a table of what are called standard reduction potentials. If you recall from Chem 11, there was something called an activity series, which showed the oxidizing power or the ease of oxidation of metals, and hydrogen was in that table. In a sense, this is the same table, just quantified by using voltages. Just have numbers now. So if you look at this table, pretty much a little under the middle you'll see in pink, hydrogen is there. See? Hydrogen written as a half reaction. And it is given arbitrarily a standard reduction potential of 0 volts. So hydrogen is called 0. So what that means is anytime you connect another metal to it, whatever voltage you measure, that's the standard potential of that particular metal relative to hydrogen. It would be as if we said, hey, let's let the atomic mass of hydrogen be 1 gram per mole. And then if we measured something and it was 4, that would mean that it weighs 4 times as much, and that happens to be helium. It's the same, similar idea here. We give the voltage arbitrarily, hydrogen is 0. And what that means is because some metals are oxidized by hydrogen and other ones are reduced by hydrogen, that means there's going to be some metals up above hydrogen and there's going to be some below hydrogen. It could have been done in different ways. This is how chemists have decided to do it. If you look at the left, it says increasing strength as an oxidizing agent. So the higher up the reactant is in this table, the more strongly oxidizing it is. And if you look at it, the top is fluorine. Fluorine is heavily oxidizing. It has a standard reduction potential relative to hydrogen of 2.87 volts. That's considered a very high standard reduction potential. Again, the standard meaning solutions, the solutes are 1 molar, and gases, the pressures are 1 atmosphere. And there's a bunch here, right? So there's like 40 half reactions shown here. We can use these values in this table to predict the cell potential of a galvanic cell. So for example, hydrogen and zinc, we got 0.76 volts in that previous figure. Let's see if I can bring that back here. See how it's 0.76? Right over here, there's your zinc. And for copper relative to hydrogen was 0.34. Well, if we come down here, look at where copper and zinc are. Copper 2 is a little bit above hydrogen. It's just 2 above. Oops, sorry, that's copper 2 going to copper 1. Copper 2 going to copper is a little bit higher. Go up around 2, 4, 5. It's right up over here. Oops, sorry. Let me see if I can make this a little bit bigger. And then maybe we can draw on this a little bit, okay? So here's our hydrogen. So here's copper 2. See what the potential difference between those two are? 0.34 and 0. So 0.34 minus 0 is 0.34. That's what we saw in that particular diagram. And then the zinc is right here, negative 0.76. So 0 minus a minus 0.76 is 0.76 volts. So we use this table to calculate cell potentials. It's really clever. It's a really nice way to make these predictions about cell potentials for galvanic cells. It's really nice, okay? So let's take a look. What I'm going to do is I'm going to take an example here. Let's do copper and zinc. So let's say that we're going to combine. Oops. Copper. And then in parentheses I'll write copper 2, because there are different forms of copper, with zinc and zinc 2. Okay, so notice we need 4 things, right? You need the metal and the ion of the metal, the second metal, and the metal ion there. Often people will say, oh, for a battery you need 2 dissimilar metals. Well, the 2 dissimilar metals would be the copper and the zinc. Okay? So let's take a look at how we would go about this. What I'm going to do is I'm going to analyze it. One, let's calculate the cell potential under standard conditions. The cell potential is the standard reduction potential of the cathode minus the standard reduction potential of the anode. So let's get the terminology down here. This is called the standard cell potential. That's the voltage of the entire galvanic cell. Think of it as a battery. What is the voltage of this battery? Okay? This is the standard reduction potential of the cathode. Okay? This is the standard reduction potential of the anode. This comes from the table. This comes from the table. This is calculated. Okay, does that make sense? You look those two up in the ones on the right, the cathode and the anode. You look those up in the table, you take the difference, and that gives you the cell potential. Okay? For a galvanic cell, it should be positive. That difference should be positive. We'll talk more about that in later sections. So first, what we need to do is we need to identify which one's the cathode, which one's the anode. And essentially, the way you do that is that the cathode is defined as where reduction takes place. And the anode is defined as the electrode, where oxidation takes place. Okay, now in practice, you look up the one that's higher in the table. It's that easy. You just look for the one that's higher up in the table, and that is the cathode. And you look for the one that's lower in the table, and that's the anode. Okay? So if we come over here, we have two choices. Here's copper. All right? I said copper 2 for a reason, so we know it's not. So we know it's that one, but not this one. So that's 0.34. The zinc, I've already put that over here, negative point. So which one's higher? The copper's higher, right? So that means the copper's going to be the cathode, and the zinc is going to be the anode. It's that easy, right? You just, the one that is higher up in the table is the cathode, the one that's lower down is the anode. So now we can calculate the cell potential so easily because now we know what they are. The cell potential is going to be the standard reduction potential of copper, I'll be more detailed, copper 2, minus the standard reduction potential of zinc 2, right? Because copper's higher up and zinc is further down. It's that easy. So it's 0.34. Just be careful you look for the signs. Negative 0.76. So you get 1.1 volts. If you're doing a galvanic cell, galvanic cells are spontaneous. You should get a positive voltage. If they're spontaneous, you get a positive. If you get a negative, that means that it's not a spontaneous reaction. We'll get into that in later sections. Okay, so there you go. It's 1.1. So that would be what would happen if you constructed a cell, okay, out of copper and zinc. So let me close that. In this diagram here, we've got zinc and hydrogen. Okay, that's zinc and hydrogen. Over here, we've got hydrogen and copper. Okay, that's copper. But if we combined copper with zinc, now we would get 1.1 volts. And look at this. Remember, hydrogen 0, 0.76, 0.34. You add those two together, you get 1.1, right? So that's the key to that stuff. So that's how you do it. You just look up this table. Of course, I don't recommend memorizing this table. I, over the years, have memorized, I think, maybe the voltages, the standard reduction potentials, I'm sorry, of maybe half a dozen of these. Like I know that copper's 0.34, and I know that zinc is negative 0.76, and I know that aluminum is negative 1.66, and I know that lithium is negative 3.05. I know those, but most people don't memorize these things, so don't worry about doing that. You don't have to, okay? Now what you'll want to do is you want to start practicing. But I do want to, in terms of, we did the numbers, right? So we calculated the number. The number here was 1.1 volts, which is, think about it, that's about a little under the voltage you'd get from a AA battery, which is 1.5. But let's just make sure that we understand what this means. What it means is that the cathode, which is positive, and this is where reduction is occurring, the metal would be copper, right? So it would be a piece of copper metal. The anode, which is negative, remember the anode is negative, and that's where oxidation is occurring. That would be the zinc, the piece of zinc, okay? So reduction is occurring on the surface of the copper, and oxidation is occurring on the surface of the zinc. Cathode and anode, those electrodes together give us our galvanic cell.